All right, here we go. Unit 6, Lesson 11. We're going to continue the work we did in class on continuous compounding and this constant known as E. So first, let's remind ourselves what continuous compounding means. That means that the moment growth occurs, so the instant that you earn interest in your bank account, you don't have to wait a year for it to compound. You don't have to wait a month. You don't have to wait a week. You don't have to wait a day, an hour, a minute. The moment new money comes into your account, it starts earning interest on itself. And so the way we defined this problem was we introduced this notation called limit notation that says the limit as n approaches infinity, right? So as n go, million, billion, trillion, keeps going, as n heads towards infinity, this expression right here, 1 plus 1 over n, right? This is where we defined the growth rate to be 100%, just as an example, to the power of n. It turns out that this is this mathematical constant called e. It's like pi. It goes on forever. It never repeats. And it's an expression that's very useful in calculating continuously compounded amounts, whether that's bacterial growth or money in a bank account. And specifically, right, there is this formula, and, you should see the outlines of it, right? We learned how E represents the case where you're growing by 100%. With some manipulation, a little bit of calculus proving, we can come up with this formula here, which is one you want to have memorized. If I ask you to continuously compound an amount, the formula here is the final amount A, so A of t, is equal to P. It's called P because of this word principal. Principal in a loan or in an interest account, it's the starting amount. That's why it's P instead of S. E is this mathematical constant E. It's a number that's approximately 2.718. R is the growth rate as a decimal. And so this is whatever percentage. If you're earning 5% a year, it would be 0.05. T is the number of time periods relative to that growth rate that have passed. So like 5 years, T would be 5. This is something, if you ever forget this, just Google continuous compounding formula. And so let's see an example of what this is going to look like on the Delta Math today. So we're going to use this formula, A equals P times E to the RT. And I know that we're going to use this formula because it says right here, my interest is compounding continuously. So it doesn't say per day, per month. It just says continuously. And so if we fill this out, A is equal to P, that's 77,000, right? The starting amount. E is not a variable. It's the mathematical constant E, like pi. It's a real number. To the power of 0.045. So that 0.045 is 4.5 divided by 100. One thing that you definitely want to watch out for here in this formula, we're used to doing 1 plus or like 1 minus here. We're not going to do that. It's just straight up the rate. So 0.045 times 12. And so this right here is the rate times the time. And E takes care of the fact that it's compounded continuously. So let's see what this one would be. Let's just open up our app on Desmos. I'll show you how you'd enter this in a calculator. You would do 77, 1, 2, 3. The letter E, you can just literally use the letter E. Desmos is smart enough to do that. To the power of, but not the number 2. What we want here is 0.04, not 2 point, let's delete that. 0.045 times, oops, we don't want that there. We want that up here. That can be a little tricky, so sometimes I just put it here. 12 times 0.045. And that amount here, we'll call this A of 12 after 12 years, would be equal to 132,000. It says to the nearest $100. So 132,000 to the nearest $100, $100. And what I really recommend every time you do one of these, just give it a gut check. Does that like pass the smell test here? If you put $77,000 in a bank account and you waited every year, is it plausible that this final amount here could be $132,000? I think so. It hasn't doubled yet, but it's been growing steadily, and it's gone up by about $50,000. That seems reasonable. And so that's how the compound growth formula works. We're going to do one more problem. We're going to do one of these ones backwards, where I give you a goal, and you try to tell me how many years will it take. So again, I'll give you the rate. I'll give you the starting amount. We're going to try and figure out the years. So let's see here. Josiah invested $96,000 in an account paying 3.5% interest compounded continuously. So I see that and I say, okay, A equals P e to the RT. Got to be working with that. So I know P. I know P is, let's give myself a little bit of room here. I know P is 96,000. E is just E. It's not a variable. The rate, 3.6% as a decimal, is 0.036. And I'm going to leave this as X because it says here, and maybe I'll do this color-coded so you can see it here. I'll leave this as X because it doesn't give me a time period. It says how long. How long would it take to the nearest year? Aha, here's the additional information for the value to reach 153,000. So I want to know, when is this equal to 153,400? And so we've done problems like this before. Remember, step one here is to try and isolate the part that has the x exponent. So I'm going to divide both sides by 96,000. On the left, that divides to make 1. So we have 96,000 on both sides. So on the left-hand side, we have e to the 0.036x is equal to, and let's do this here, 153,400 divided by 96, 1.59. So it's grown by about 60%, 1.598. We'll call it 1.598. That should get me close enough here when we round. And so here again, we're faced with a dilemma, is how do we solve for that x? So what I'm going to do is I'm going to introduce you to something called the natural log. So the natural log, or as we say in French, the log naturel, right? And that's why we have this ln. It comes from the French. That's why it doesn't say nl. It says ln, just like it would in Spanish, right? The adjective is in the opposite of order of how we do in English typically. And so you'll hear even me sloppily pronounce this as ln, but it's really better to just say the natural log. And so this phrase right here, the natural log of x, what is it? It is just a special base of log, the log base e. So remember, right, we have like the log base 2 of x, and that means 2 to what power is x? And I said, remember, if there's nothing there, it's an understood 10. Well, it turns out this natural log, all it is a fancy special term for the log in base e. It's such an important number, e is, that it gets its own log base. We call it natural log. And so it means what power of e gives me x. And so if I wanted to solve this equation, e to the x is 20, I would say, let me take the natural log of e to the x, and that would be the natural log of 20. And the reason that this is super helpful, right, is that this question, it's kind of like a silly riddle. Natural log means what power of e. And so this is saying what power of e, that's what this is saying, is equal to e to the x. Well, it's kind of a stupid question. It's just x. E to the x is e to the x. And so the natural log of e and e to the x cancel each other out, and we just get x here. So that's why x would be the natural log of 20. X would be the natural log of 20. Another way to see this, if you got here and you didn't quite remember that part, you could say the natural log of e to the x is the natural log of 20, and you could use exponent rules. X times the natural log of e is the natural log of 20. And when you type this into your calculator, this is 1. Why is it 1? Because it's asking the question, what power of e is e? And the answer is 1. That's why natural log and e to the x kind of cancel each other out there. Anyway, long story short here, what we end up doing is we end up taking the natural log of both sides. We take the natural log of both sides because that will tell us what power of e is 0.036x. It's just 0.036x. So again, natural log and e undo each other. They're inverse operations. This is the natural log of 1.598. And so what we have here, final answer, we divide by 0.036. We divide by 0.036. This right here is your perfect final answer. Now all we have to do is go over to our calculator and type in the natural log, and it should be somewhere around here. If you go to functions, miscellaneous, here it is. Let's see, natural log right there. Natural log of 1.598. And we're going to divide that by 0.036. That's going to get us about, it says to the nearest year, about 13 years. 13 years will be how long this takes. You could plug that back in for X to test that one out. All right. So key points here to remember. Number one is this compound interest formula. You're going to need this. If you forget it, Google it, write it down, put it on a sticky note. You're going to need it for all the problems today. The first problems you're just plugging in. The second problems require an understanding of this natural log and an understanding that natural log and e to the power of x undo each other. You could also do this with log base 10s and just use this trick here. That trick would totally work. And so if you get stuck here, don't forget you can just take the log of both sides, move the exponent out front, and you can work the rest on your calculator. But if you just remember that the natural log of e to whatever is here just equals that number, it'll save you a lot of time.